Hello and welcome to FRSC 2110 Fire Service Hydraulics. My name is Adam Roberts and I'm your instructor. Even though this is not a live lecture, please remember you can contact me anytime by email at aroberts@athenstech.edu or call me in the office at 706-357-0162. Also look in Blackboard Collaborate on the calendar in lessons for my virtual office hours where we can meet and discuss any questions that you may have about the material. Now, I don't want you to get overwhelmed. It does seem like a lot, especially in this first chapter, but it does get better. My advice to you is focus on the definitions and the key terms for each chapter, as well as the review questions. Make sure you memorize the formulas for each chapter. You will have math problem assignments for each chapter. However, I will not require you to do hydraulic calculations for your exams. What do you say we go ahead and get started with the objectives? Discuss the various characteristics of water, the basic elements of fire, compartment hydraulics. Explain various effects that steam expansion has on the ability to purge an area of smoke and noxious gases. Discuss the advantages that water has as an extinguishing agent. Recognize some of the disadvantages that water has when used as an extinguishing agent. Understand and discuss the 4 characteristics of water that affects its use in fire protection. Identify the weight of 1 cubic foot of water, the number of gallons of water in 1 cubic foot, the weight of 1 gallon of water, the number of cubic inches in 1 cubic foot, the number of cubic inches in 1 gallon of water, the weight of a column of water measuring 1 inch by 1 inch in base by 1 foot high, and the weight of a column of water measuring 1 inch by 1 inch in base by 2.304 feet high. Define both force and pressure. Explain the basic differences between pressure and force. Understand the differences among static pressure, flow pressure, and residual pressure. Explain the 6 basic rules governing the primary characteristics of pressure in liquids. Define head. Determine the pressure when the head is known. Determine the head when the pressure is known. Understand the effects of elevation on pressure. Define back pressure and forward pressure. Be able to determine the back pressure or forward pressure when the lines are laid either uphill or downhill. Determine the force on the base of a container. Understand and work problems involving the force on clapper valves. Explain Bernoulli principle. Explain the meaning of conservation of energy. Define energy, potential energy, and kinetic energy. Illustrate a venturi in a pipe. Hydraulics is defined as the branch of physics dealing with the mechanical properties of water and other liquids and the application of these properties in engineering. In the scope of fire department hydraulics, the portion of general hydraulics that pertain to water and its use in firefighting and fire protection. In the fire service, water is the primary extinguishing agent because it's one of the most abundant sources on earth, and it has great properties that allow to extinguish fire. However, several properties of water affects its heat absorbing ability. It's important to note that water freezes at 30 degrees Fahrenheit at a normal sea level pressure of 14.7. The ice that is formed will start melting at 32 degrees Fahrenheit. As we know, water is an element, and it can be a solid, liquid, or gas. When it changes form, the water becomes more or less dense. When 1 pound of water freezes at 143.4 BTUs, and that's the British thermal unit of heat, are released. When 1 pound of ice melts into water, 143.4 BTUs are absorbed. Both of these examples are referred to as the latent heat of fusion. What this formula, or this example, is supposed to illustrate is the fact that latent heat of fusion is the amount of heat absorbed or released by a substance as it passes between the solid and liquid phase. Latent heat is measured in BTUs, or calories per unit weight. It's important to know that fire is energy, and energy cannot be destroyed. It can only transfer form. So by adding water to a fire is in turn absorbing that energy and that heat and transferring the water into the form of gas, thus putting out the fire. One BTU is defined as the amount of heat needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. And on the metric side, 1 calorie is defined as the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. This is known as the specific heat of a substance, which is the amount of heat required to raise the temperature of 1 pound of a substance 1 degree Fahrenheit, or the number of calories required to raise the temperature of 1 gram of the substance 1 degree Celsius. Now, why is this important in the fire service? Basically, it is a way to determine how much water is needed to extinguish a given fire with a specific type of fuel load. From a firefighting standpoint, the specific heat of a substance should be thought of as its thermal capacity, or ability to absorb heat. The specific heat of water is 1. To raise 1 pound of water from a temperature of 60 degrees Fahrenheit to 212 degrees requires 152 BTUs. So that is a lot of energy. And what happens when you raise water to 212 degrees? It turns from a liquid to a gas, or steam. The amount of heat required to convert 1 pound of water into steam is 970.3 BTUs. This is referred to as the latent heat of vaporization, which is the amount of heat absorbed or given off as a substance passes between the liquid and gaseous phase. Now, it's important to note that when you're heating up water to 212 degrees, it requires a certain amount of BTUs. But then changing it from a water to a gas requires a whole lot more. This is illustrated as follows. Water weighs approximately 8.33 pounds per gallon. And we go ahead and just round it up to 8.35 pounds per gallon for hydraulic calculations. So here's the question. How many BTUs does it take to raise 1 gallon of water from 6 degrees Fahrenheit to 212 degrees? And the answer is 1,266 BTUs. And that is because we're taking the weight of the water, which is 8.33, and we're multiplying it by our constant of 152. As we saw in previous slides, it takes 152 BTUs to raise 1 pound of water from a temperature of 60 degrees to 212 degrees Fahrenheit. Again, 8.33, or I should say 8.35, is our constant, because that's the weight of the water, times our constant, of 152 is how we get the answer for this question. The amount of heat required to convert 1 gallon of water from a liquid to steam is approximately 8,082 BTUs. This is illustrated by the weight of 8.33 times our constant of 970.3. So again, remember this is our weight. And this is our constant. And I apologize that this is not looking very good. So you can use this as a ratio or a proportion, shall we say, to figure out other math problems by knowing this variable. So we know that 1 gallon of water is 8.33, and it takes 8,082 BTUs to convert that liquid to steam. So, what if we had 2 pounds of water and we wanted to convert it to steam? How much BTUs is it going to take? First, we have to figure out the weight of the water. And if we know that 1 gallon of water weighs 8.33, then we times that by 2, we know that our new weight is going to be 16.66. And we put that over x, because this is going to be our unknown, because we're trying to figure out how many BTUs. So 16.6, and all we're doing is cross multiplying, times our constant 82, divided by 8.33 will give us our answer. So 16.66 times 82 equals a very large number, 1346.12, and then we divide that by 8.33, and that gives us 16,164 BTUs. Remember, keep your weight on top, BTUs on the bottom. It should be noted that nearly 6.5 times as much heat is absorbed during the process of vaporization than is absorbed in the process of raising the temperature of 1 gallon of water from 60 degrees to 212 degrees. So when water is being converted to steam, it is using a whole lot of energy to do this, thus lessening the flames and putting the fire out, because it's absorbing all the heat, it's absorbing all the energy, and it's turning that flame from that flaming state, transferring that energy to the water, turning it to gas that increases the surface tension, thus putting the fire out. Another factor of importance that occurs when water is changed to steam is its tremendous expansion. So when that water turns to the gas and steam, basically, the expansion ratio is approximately 17,000 to 1 at normal sea pressure at 14.7 psi and 212 degrees. At 500 degrees, and that's a pretty common temperature that you would find at a fully involved type fire on some sort of flammable material, the ratio is 2,400 to 1. And at 1200 degrees, the ratio is 4,200 to 1. So we will use the calculation of 17,000 to 1 for our calculation as our constant. So 1 part of water will expand 1,700 times at 212 degrees at the normal sea pressure of 14.7. So when water expands like that, it has a smothering effect, and it suppresses the flame. It is the cooling effect that actually extinguishes the fire. With all the advantages of water as an extinguishing agent, there are some disadvantages. So we looked at the fact that, hey, water absorbs a whole lot of energy, especially when we're changing it from a liquid to a gas, thus taking away the energy and converting that energy from a fire to steam. So let's look at some of the disadvantages now. And we know water is, the most abundant source on Earth, and it's a great cooling effect as well as a smothering effect, thus blanketing the flame and help to prevent combustion by preventing oxygen to getting to the fuel source. So here's our disadvantages. The surface tension, which is basically how the water will sit on top of an object, okay? So if you take a drop of water and you put it on a table, it's just going to sit there and bubble up. And that's an example of surface tension. And that basically means that the object it's on has low permeability, meaning the water will basically stay on top of it. Now you take that same drop of water and you drop it on, say, a tissue paper, it's automatically going to go from that drop being absorbed by the tissue in a hurry. So the surface tension, which limits the water's ability to penetrate some materials such as upholstery, fabric, and ballet cottons. The conductivity, which creates the possibility of electrical shock, is also a disadvantage. And violent reactions may occur with certain chemicals, such as the fact of magnesium. You take magnesium, which is a metal, you add water to it, and it's going to cause that magnesium to kind of explode and send out sparks and showers. And a good example of magnesium are sparklers. Sparklers are basically made of magnesium, and that's why it gives it off that showering effect. And you need copious amounts of water to put those things out. For example, an engine block in the old VW Bugs are magnesium based, and when they catch on fire, you add water to it, it's going to cause an explosion type reaction, and then it takes, again, copious amounts of water to put that fire out. A lot of times with those types of materials, a powder extinguishing agent does better. Water also has a low viscosity, which allows rapid runoff and limits the ability to blanket the fire. Of course, as we said earlier, water can, will, and does freeze. And it can potentially damage the products or things in the room that you're applying the water to, especially electronics. In its addition to its extinguishing capabilities, several characteristics of water affects its use in fire protection. You got to remember, water may be found in a solid, liquid, or a gas. Constant thought must be given to the possibility of water supplies becoming unavailable during freezing weather. Now, it's important to remember that the colder water is, the heavier it's going to become. So water is more dense at freezing at 31 degrees as opposed to 6 degrees Fahrenheit in its natural liquid state. And it becomes even less dense at 212 degrees, where it begins that process of turning into steam. And what I mean by dense, of course, is the weight. Now, this will make more sense on the next slide. But water seeks its own level. As water seeks its own level, it creates a pressure at any point where it is stopped from accomplishing this objective. So when we look at it here, we have water flowing into side A. And as we see, the water is attempting to go across and reach the same constant level as seen in B. At any point that water is stopped from going up, it's going to start exerting pressure on that object because it wants to become even. So for example, if there was a line right here preventing the water from going up here, and all the other ones are there, it's going to be exerting pressure here, trying to force it up. That way it is equal across all three sides. Water is practically incompressible, meaning you take water and you try to smash it and it ain't going to happen. You know, it's just going to spread out. And it actually requires a pressure of 30,000 psi to reduce the volume of water by just 1%. So that would be like taking water and putting it in a container, a sealed container, and if you wanted to reduce its size by 1%, you would have to push down on the top of that container with 30,000 psi. So here's our container, here's our water. And again, if we wanted to just reduce this by 1%, it would require us 30,000 pounds per square inch of pressure to just compress that down a little bit. The density of a substance is defined as its weight per unit volume. The density of water varies, as I said, with its temperature. Water is at its max density at a temperature of 39.2 degrees Fahrenheit. At this temperature, it weighs 62.4 pounds per cubic foot. Okay, so some more constant calculations to remember. A container measuring 1 foot by 1 foot by 1 foot has a volume of 1 cubic foot. If a 1 cubic foot container is filled with water, it will weigh approximately 62.5 pounds. Okay, so here's a math problem for you. If 1 cubic foot container is filled with water, it weighs 62.5 pounds. How many gallons is that? Now, from previous slides, we know that 1 gallon of water weighs 8.35 pounds. Notice how we got the pounds on the same sides, right? And we have gallons at the top and pounds at the bottom. So again, we're just going to do the concept of cross multiplication. So 1 times 62.5 pounds equals 62.5, right? So then you take that and you divide it by 8.35, which gives us 7.48, or if you want to round it up, 7.49 gallons in 1 cubic foot of water. And as we already figured out, if the water from 1 cubic foot container is poured into 1 gallon bottle, it will fill approximately 7.48 bottles. So there are 7.48 gallons in 1 cubic foot. The water in each gallon bottle will weigh approximately 8.35 pounds. All right, some more constants here. 1 cubic foot is measured in inches, which is 12 inches by 12 inches by 12 inches. The total number of cubic inches is 1,728, and that's basically multiplying 12 times 12 times 12. 1 gallon of water contains approximately 231 cubic inches. So, if 1 cubic foot is divided into units, that measures 1 inch by 1 inch by 1 foot high. It will contain 144 units. The weight of water in each of these units is 0.434 pounds. For one of these units to weigh 1 pound, it would have to be a height of 2.304 feet. So, some key terms to remember. Force is the amount of energy applied at a given point or points. Force is usually expressed in pounds. Pressure is force per unit area. Pressure is expressed in PSI for the fire service and may be considered as a measurement of energy in water. So this all comes about, and to bring it full circle for those that don't know, is the reason we're going over this is how much pressure is required at the fire truck to push out the water, from the hydrant in the ground, from the fire truck to the end of the nozzle to get the appropriate amount of water on the fire to extinguish it. It is important to understand the relationship between force and pressure. A column of water 2.304 feet high that measures 1 inch by 1 inch at the base will create a pressure at the base of 1 pound. So this is our 1 inch by 1 inch, and it's 2.30 feet high. And here at the bottom, because the water is poured in, of course at the top, fills our container, will exert at the base, down here, 1 pound of pressure, or 1 PSI. That container, having a 1 foot square base that is 2.30 feet high, will house 144 of those little 1-inch columns. Since the pressure on the base of the container is 1 psi, the force is 144 pounds on the total area. And what it's basically doing is adding up all those little, inch columns of water, and that's the force. The actual thing's doing the pressing down on that base of that column. It's just breaking everything down into the smallest unit of measurement. Okay, more key terms. Static pressure is the pressure of water when it is not in motion. Flow pressure is the pressure of water after it has been placed in motion. And residual pressure is the pressure remaining at the hydrant outlet after water is flowing. So, this is our fire truck. Here's our hydrant. We have lines going to the fire truck. And then we have lines going out. To the end of our nozzle. And here's you, our friendly firefighter. Squirting the water. Now, if the water coming from the hydrant and then coming into our truck going out here is stopped. Oh, didn't mean to erase that. But if the water is stopped from flowing, then the water in the line here that has no pressure putting on it, because it's stopped, is going to be static. So that is the pressure in this line. Again, we have our fire truck here. It's got the lines coming out. You're at the end, and you have not opened the line yet. The pressure in that line is said to be static. Now, once you, hopefully not get burned here being so close to the fire, begin flowing water through your nozzle, then that water is no longer static. It's moving from our hydrant to our truck through the hose to the fire. And that is what is our flow pressure. Now we go back over here to our hydrant. And boy, that's a sad looking hydrant. The water that's left in the hydrant down here that's not actively being used will exert pressure, and that is known as your residual pressure. So we have 6 principles of pressure that we deal with in hydraulics, and it will behoove you to remember these 6. 1. Fluid pressure is perpendicular to any surface on which it acts. Basically, it will put pressure on all sides of the container. So again, here's our container. Filled with water. It will exert pressure on all sides. The pressure at any given point in a fluid at rest is of the same intensity in all directions. With the nozzle closed, going back to our little scenario with fire truck, and a pressure of 60 psi, that is static in that hose, it will be transmitted throughout the entire hose at all points. So if we have 60 pounds coming in, 60 pounds coming out, that's not going anywhere, you will have 60 pounds of pressure on every square inch of that fire hose. So again, if this is our fire hose, notice we have 60 pounds of pressure in here. Across A, B, and C, it's all going to be the same when it is static. Now remember we said it was virtually impossible to compress liquid. And here's the reason why. External pressure applied to a confined liquid is transmitted undiminished in all directions. If the pressure in the line is increased to 80 psi, it is transmitted everywhere throughout the entire hose. The downward pressure of a liquid in an open container is directly proportional to the depth of the liquid. And principle 4 basically is saying that the pressure at the bottom of a container is going to increase dramatically the deeper it is, or the higher the container is. So we have our container, and we say that that's 2 foot high, filled with water, will have a set amount of pressure. And then we turn around and make a bigger container that is, say, 11 feet high. The pressure here at the base will grow exponentially, meaning get heavier. Here's a great example at 20 feet, and then another at 40 feet, how the pressure is going to increase. And again, the pressure will increase on all sides. Principle number 5. The downward pressure of a liquid in an open container is directly proportional to its density, or basically, its mass, its weight. Mercury will weigh more than water because it is more dense. So with liquids, the heavier it is, the more dense it is, the more it's going to weigh. Principle 6. The downward pressure of a liquid on the bottom of an open container is independent of the shape or size of the container. It is the height above the opening that counts. So the way to think about this is our containers, our water tanks. No matter the size or the shape of the top, the pressure at the bottom here will be the same if they're both the same height. However, if we have this one 14 feet high and this one 12 feet high, the 14 foot high will exert more pressure at the base. Now, the pressure at that base is known as the head pressure, which is the vertical distance from the surface of the water to the discharge or the opening below. How high is the water level above the discharge opening? So again, here's our great little fire truck, and it's on top of this nice big green mountain here, and let's say that it is 20 feet high. So that pressure down here at the nozzle waiting to go out will be increased, and that is known as the head pressure because it's at the discharge opening. And when you look at our municipal water supply systems, they're either pump fed or gravity fed, and meaning that either pumps pressurize the lines under the ground, or you have gravity doing it for us. So here's an excellent example how you have your water supply and reservoir being, say, 120 feet high, or a water tower 120 feet high, and it's pressurizing the line because of our principle of the water getting pushed down. And then, of course, the pressure down here is known as the head pressure. So let's dive into another math problem. Determining pressure when the head is known. The pressure is directly proportional to the head. So for each foot of water above the discharge opening, 0.434 psi is created. Or in fire service, basically we use 0.5 for round numbers. Okay, so let's do our first math problem here. We have 120 feet, and we're trying to figure out the head pressure. Feet, pressure. We know that 0.5 pounds per square inch for every foot. So here is our cross multiplication. Now don't forget to do your decimal, otherwise it's going to mess you up. So basically it's 120 times 0.5 divided by 1 is going to be 60. So 120 times 0.5 is 60, and then of course 60 divided by 1 is 60 pounds per square inch of head pressure right here. So here's our formula again. The formula for finding pressure when the head is known is pressure equals 0.434 times the height. And again, I say use 0.5 for round numbers. I'm not going to gig you guys if you show your work and you use 0.5 as opposed to 0.434. To me, it just makes it a little easier. So now here, this is kind of reversing it. So we already know how many feet it takes to create 1 psi. So what is the corresponding height? So basically, for every 2.34 feet, it's going to be 1 psi as a whole. Or again, I say in round numbers, 0.5 per 1. Alright, so let's work this problem out. And our formula here is H equals 2.304 times P. And P is pressure, H is height. So a good way to illustrate this is we know that 2.30 feet equal 1 pound per square inch. They gave us 75 psi as the head pressure. So 2.34 times 75 divided by 1 gives us our answer of 172.8 feet high. Taking this knowledge, this is what's going to help us figure some added pressures. So, what we have to look at is something known as elevation pressure, a loss or a gain whenever the nozzle or the discharge opening is above or below the pressure source. So, if the nozzle is below the pressure source, we're going to gain pressure because it's going to be going downhill. If the nozzle is uphill, you're going to lose pressure because it's going to require more energy to overcome gravity. Right? For this class, back pressure is when the discharge opening is above the pump. And forward pressure is when the opening is below the pump. So that's how to help you differentiate between pressure loss and pressure gain. So back pressure is when the discharge opening is above the pump, meaning you're going to lose pressure because it's going to go back down the hill. And forward pressure is when it is above the pump. Now, is this going to create forward pressure or back pressure? Okay, the answer is going to be back pressure. Now let's figure out how much back pressure it's going to create at 85 feet above the pump. Okay, so we know 1 foot gives us 2.304 pounds per square inch. This is 85 feet above. And this is going to create back pressure because it's higher, right? So 85 times 2.304. Again, we're just cross multiplying. Will give us a back pressure of approximately 195.84 psi on the pump. So the pump is going to have to work tremendously hard to get water out of that nozzle from the fire truck. So it's going to have to overcome about 200 pounds of pressure just to get water to come out. And that's the concept of friction loss. So, instead of looking at hills and mountains and valleys, let's look at multi-story buildings. That's more common what we're going to face. Now, there is no set standard for the height between floors on high-rise buildings. Some can be as much as 14 feet, and others can be as little as 10 feet. So for this class in text, we will assume that for each floor, there is 12 feet difference. So if we're saying there's 12 foot per floor and there are 5 floors, how many total feet high is this building at the roof? Very simply, 12 feet times 5. We're saying that this building is a total of 60 feet high. So for each story in height, we're going to go ahead and assume that the back pressure of 12 feet is 0.434, which equals out to be 5.2 psi, or pounds per square inch. Basically, 5 pounds per story. Again, I'm okay if you use 5 as opposed to 5.2 in your math problems. Just make sure that you show your work, okay? Alright, so some things to keep in mind. Since we are already on the first floor, you do not include the first floor in figuring your back pressure. So, your question, for a 5-story building, what back pressure will be assumed? So we go 5 stories minus 1, because we're on that one, so that's 4 stories high. And then for every story, you're assuming that you have 12 feet. So 4 times 12 is 48 feet. So 48 feet times 0.434 for pressure will equal 20.8 psi of back pressure. Or if you used 5, then you're looking at 24. So again, I'm going to give you a leeway with the rounding. You're looking at about a 5 psi swing either way. Okay, so here's your problem. How much back pressure are you going to have to overcome to get water to flow out of that pipe at the top? We know that that is 99 feet high. Since we're on the first floor, we're going to say that this is only 8 stories, because we're counting, right? 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 12 is 96 feet. And then 96 feet times 0.434 will give us a back pressure of 41.7. Okay, let's start working the other way now. Forward pressure. Forward pressure is created when the discharge again is below the point. The formula is the same. Forward pressure equals 0.434 times the height. If a pumper is at the top of a hill and the line is extended down the hill and the elevation difference is 100 feet, what will the forward pressure be? Okay, so simply put, 0.434 times the height, which is 100. Basically, you're moving your decimal point over 2 spots. Anytime you multiply by 100, which gives you your answer of 43.4. Now this is forward pressure, so this is not a negative, this is a gain. So you will gain 43.4 pounds per square inch for every 100 feet. So, lines laid uphill or downhill. Lines laid uphill or downhill are said to be laid up or down a certain grade. For example, a 10% grade rise of 10 feet in height for every 100 feet of length. So, a 12% grade rise, how far for every 100 feet in length? And that's basically 12 feet. So if you put that in mathematical terms, remember 10% is 0.10, 0.10 times 100, and that's how they get 10 feet. In our problem at the bottom, we have 12%. How far for every 100 feet of length? So again, that's 0.12 times 100, and that's how they get the 12. Okay, so here's your question. You have a fire truck pumping up a 12% grade, 700 feet of hose. How many feet high is it? And it actually shows you 84. So that's basically figured out by saying, and this slide's wrong because this actually should be 700 feet. 700 feet of line laid up at 12% grade. What is the height? And we know a 12% grade per 100 feet is going to be 12. So 7 times 12 equals 84 feet. And then we know that back pressure is 0.434 per foot. So that's a very simple 84 times 434. Don't forget your decimal, right? So 84 times 0.434 equals 36.45 or 0.46 if you round per square inch. All right, before we move on to the next set of problems, some things to remember. Remember from earlier the difference between force and pressure. To figure the force on the base of a container, we multiply the PSI by the area of the base. So our formula is this. Force equals pressure, that's in PSI, times area of the container. Pressure is going to equal, so you got to do a little algebra here, 0.434 times the height. And height, of course, will always be in feet. And the area is done in square inches. So basically that's, 12 times 12, depending on the size of the container. Okay, so we're going to have multiple steps in solving this particular problem, remember. So let's go ahead and break this down with the first step. So our container is 5 feet high. What is the pressure going to be? And our formula for pressure is P equals 0.434 times height. So P equals 0.434 times height. Our height is 5 feet. So 434 times 5 equals 2.17. And that is what? 2.17 pounds per square inch, or pressure. Don't forget to mark your measurements so you don't get confused. So let's look at this one now. Don't let it throw you. Okay. So first, let's look at the area. Okay. The area of this container is going to be 4 times 2, which is what? 8. And then 8 feet. So what we want to do is change that to square inches, because area is always square inches. So that's 8 times 144. So 8 times 144 gives you a total of 1,152 square inches. So now that we have our square inches, that gives us that 1,152 square inches. Now we're going to multiply that by the pressure that we figured out earlier, remember? So that was 2.17. So 2.17 times our area in square inches, don't forget to do the conversion, will equal 2,499.84 pounds. And again, force will always be in pounds and pressure will always be in PSI. So that's a good way to remember the difference. Force is in pounds, pressure is in PSI. Okay, so moving on to our next objective in determining force on a clapper valve. First, we got to figure out what the heck is a clapper valve. And a clapper valve is an automatic valve installed in some sort of hydraulic system that permits the flow of water in one direction only. Clapper valves are used in sprinkler systems, standpipes, and Siamese appliances. Now remember, water always wants to be equal and spreading out, so to help it from spreading out, that's why you have that clapper valve in there. So you look on page 23, figure 1.39 gives you a good illustration of this. Clapper valves are open or closed depending on the difference in force, not pressure, force. So as illustrated here, you have water pushing on a clapper valve, forcing it shut. You introduce water on the other side, and once it gets enough force behind it, the clapper valve will open, permitting the water to flow through. So let's look at the force on a clapper valve, and you can see this on page 24 in the text. And what you want to figure is the clapper valve shown in figure 1.40 has an area of 100 square inches on one side and 90 square inches on the other side. If the pressure holding the valve closed is 30 psi, what pressure will be required on the other side to open it? All right, our answer: to open a valve, a force greater than the holding it closed must be provided. The force holding the valve closed is what? 30. So force equals P times area. Force equals P times area. We know the pressure holding it shut is 30 psi. Our area, which is already in square inches, is 100. So 30 times 100 equals 3,000 pounds. So now if we want to change that and figure out the amount of PSI it's going to require, because remember, we're looking for pressure. So pressure is equal to F over A. Pressure equals force over area. Now we figured out the force was 3,000 pounds. And again, we know our area on the other side, which is what? 90 square inches. And you can get that by looking at the chart. So 3,000 divided by 90 equals 33.5 psi. And that is the amount of pressure that will produce enough force to open the clapper valve. And the reason being is because that valve on that side has a smaller square inch. So we increase the pressure, which will increase the force and open it up and allow the water to flow. Okay, Bernoulli's principle. And this is what's going to help us figure out the clapper valve, what force is going to take to open it. As the speed of a moving fluid increases, the pressure within the fluid decreases. The principle behind is the law of conservation of energy. Remember, energy can neither be created nor destroyed, but merely change form from one to another. In figure 1.41, the water in the horizontal pipe has two forms of energy, potential and kinetic. Now, potential energy is the energy potential it has standing still. Like a book on the table has potential energy. Once you push that book off a table and it begins to fall, it now has kinetic energy. Okay? The Venturi effect is fluid flowing through a constricted section of tube which undergoes a decrease in pressure. And this will all make sense here in a minute. And there's an example of your Venturi principle. The application of Bernoulli's principle basically is the design of an aircraft wing. The Venturi effect in a foam inductor is the same in 1.43. Okay, so the reason they want you to know about Bernoulli's principle and the wing being similar is the fact that in firefighting, sometimes we use what is known as a foam inductor. And the foam inductor operates off of Venturi principle, where foam concentrate, this goes, the line going to, say, our foam bucket, is drawn in to the line here to be administered and put on fire to help put it out, whether it be a chemical fire or a woods fire. You have a valve here that'll set it to what percent you want, usually 6 to 3%. And the reason that fluid will come out of that bucket into the line is Venturi, because the pressure coming in here gets siphoned down or knocked down into a smaller size outlet, creating a Venturi principle or a suction where this draws that fluid in. And then it gets all mixed around and, of course, out it goes. Okay, gang, we covered a lot, and I do mean a lot here in Chapter 1. So go ahead and work on your review questions. You've got a whole bunch of math problems to go over. And if you have any trouble with them, either A, hit me up by email and we'll go through them, or B, you can look at my virtual office hours in Blackboard on the calendar, and we'll go into Collaborate and we'll work this stuff out together so you get a good understanding of it. Until then, I hope you guys have a good day. Thank you. Oh, and before I forget, remember you can email me at aroberts@athenstech.edu, or you can call me in my office at 706-357-0162. Thank you.